Okay, so we're back for part 2 of polyphenol oxidase, in this case inhibiting, starting off by talking about inhibition using citric acid. It's an example of chelation. A little bit of ancient Greek for us first. The word chelation is derived from the Greek chela, meaning claws. Molecules that do chelation can be said to grab other molecules or parts of molecules in claw-like structures. Hence the picture of the crab. We need to look at a bit of basic organic chemistry first. You are probably familiar with the fact that a covalent bond forms when two atoms each donate an electron to a bond. In the case of coordinate bonding, which is involved in chelation, one atom, often a metal, donates both electrons. Now remember, polyphenol oxidase has a copper atom, several copper atoms indeed, as in fact do most enzymes. Most enzymes have metals at their cores. Okay, so this process of coordinate bonding is sometimes called dative bonding, and this is what happens during chelation. And here's a good example. Ethylene diamine, often in the form of ethylene diamine tetracetic acid, EDTA, is involved in chelation reactions. EDTA is often used in food. Here ethylene diamine forms two coordinate bonds with a generic metal designated M. This involves a claw-like molecular structure. The electrons donated in this case come from the nitrogen atoms, which is why we'll look at why this is possible in a minute. You might want to think now about how this will affect the action of PPO. So again, some basic chemistry. We can draw the nitrogen Bohr form in the Bohr form here. It has two non-bonding electrons in the inner shell and 5 in the outer shell, but nitrogen only forms 3 bonds. This leaves 2 spare electrons. These are said to be a lone pair of electrons. They're used in the formation of coordinate bonds to metals and also in influence structure as well. And there's an example of how it happens. The lone pairs here coordinate to the metal. So to go back to the earlier question, if ethylene diamine or another chelator forms coordinate bonds to the copper atoms in polyphenol oxidase, this prevents the enzyme from carrying out its reaction. As I'm sure you know, most enzymes, when they react, change their shape. If chelation has taken place, this shape changing can't take place and the enzyme can't do its polyphenol oxidase reaction. Here's another example of a chelator. Citric acid, in this case from lemon juice, as we discussed a few times before, is another chelator that inhibits PPO in a similar way. In this case, the electrons are donated from oxygen lone pairs, and there's the Bohr forms for oxygen shown there, plus the 2 lone pairs. Oxygen forms 2 bonds, again leaving 4 spare electrons, which form 2 lone pairs. The most widely distributed oxygen-containing molecule is water, of course, and is bent because of the influence of these lone pairs. But in this case, we're interested in the chelation effect on the copper atom at the centre of PPO. Okay, so thermal inactivation. This is fairly straightforward. Like all enzymes, PPO can be permanently deactivated by heating. Proteins are highly specifically folded, and this one is, in this case, specificity is distributed by heating, so they can't carry out their reactions, nor can they be spontaneously refolded back into an active form. As I mentioned before, blanching is a cooking process where fruit or vegetable is briefly immersed in boiling water and acts to denature PPO, at least in the surface layers. Okay, this slightly blurry graph from this particular paper shows the effect of temperature on PPO activity on a range of phenol. We'll notice that activity rises to a maximum around 30 degrees C, then falls off rapidly. So this is taken from PPO is taken from wild mint. So there's a paper there. Okay, pH inactivation of PPOs. All enzymes have an optimal pH, just like their own optimal temperature, and that can be quite a narrow range. And outside that range, activity drops off rapidly, again because of the shape of the enzyme changing. It can't work in the way it's supposed to. It wasn't there for some reason. The pH optimum for wild mint is more complex than the graph seen for temperature, but you can see the fall of activity both below and above the pH maximum is pretty clear. So here's something new. Apples that don't go brown. A new approach. This genetic method is well outside the scope of this module, but links are provided here for further reading. there's a video there showing this apple which has been engineered by something called gene silencing, which deactivates PBO. And there's a timer there showing the conventional apple versus what's called the Arctic apple. Well worth having a look at it. It's quite an interesting development. So there we are. That's all, folks. That completes our discussion of enzymatic browning. Thanks for listening.